How do we know that there was a Big Bang? And what the heck is it? Interestingly, the how question was solved in 4 different independent ways about the Big Bang. This is the best that science has to offer, actually. It's called independent confirmation. The first evidence for the Big Bang is actually a weird fact. The same way as when you ask why is the sky blue, you may ask why is the night sky black. And the answer to that has to do, believe it or not, with the Big Bang. Second support is the receding of galaxies. The third is the isotopic abundance of elements. The third is, that's the third. And the fourth is the microwave background radiation and its fluctuations. And that lecture will explain all of them. The last line here, the acceleration of the universe, is not one of those 4 pillars on which the Big Bang is standing. Rather, it's a recent discovery that we are still trying to fully understand. So what is the Big Bang, really? I am letting you read here. So yeah, the Big Bang is the now well-established theory that what is now the observable universe was once smaller, compact, dense and hot. Nothing more, nothing less. By now you know that if we see as far as 100 trillion meters away, that's a distance that light would take about 13.7 billion years to reach us, which means that's 13.7 billion light years. Now that's the size of the observable universe. That's what we mean by the observable universe. It could be that there is something further still, but we can't detect it and we can't tell. So the Big Bang only relates to that part of a possibly larger universe that is now of the order of 10 to the 26 meters that was once much smaller and hotter. I'll remind you that this picture is all galaxies. We've seen it in the first lecture, we also saw it a couple lectures ago. It's all galaxies except for 3 stars that have kind of cross shapes on them. This is a result of the technology used with this specific telescope. And that makes it easy because you say, except for those stars, all of those dots and splotches are galaxies. So why are there dark regions between them at all? Come to think of it, why isn't the night sky glowing with light? This is what the night sky should have looked like. Just very dark, if there were no stars at all. But if there are stars all the way to infinity, if there are galaxies all the way to infinity, the night sky should be aglow with light. Think about this cartoon picture. If a line extends to all stars or all galaxies, and if the universe is infinite in size, that means that light comes along that line. So you can't have a line that goes and goes and goes and there's no source of light behind it. So there should be light coming from every point in the sky. You may say, hey, we learned a little bit more about light than that. We learned that light becomes dimmer as it reaches our eyes. Not only that, we learned that the brightness drops. It drops, for example, to 1/4 when the distance is doubled from the source. Well, that was because that light is spread all over a sphere. But if you look at the sphere on the right, within that sphere, there is way more sources of light. How many more? Exactly the same as that factor 4 that we just discussed. So there are 4 times as many when the sphere is 4 times is twice as large. So it kind of cancels out. So every shell surrounding us would give the same amount of brightness, and if there are infinite number of shells, that means the night sky would radiate, unless there aren't infinite number of shells, unless the universe was finite in size. Of course, there are slight ways around it. If the universe was infinite, for example, what if light got tired? Well, that's a problem there, because we learned about energy and energy being conserved. Light can't get tired without the energy changing into something else. And that something else would make things eventually go up in temperature and glow. The person that came up with this paradox, Olbers, an astronomer in the 19th century, actually thought of dust. But that was his solution, and it was wrong. So, as usual in these lectures, I'll give you a few seconds to try and come up with the correct answer here. And once you do, click and see if you were right. Bum, 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 bum. Here comes the next and much more sturdy pillar of the Big Bang. Edwin Hubble, the same guy that figured out that other galaxies were not in our own galaxy. That same guy that used Cepheids, those things that were discovered by Henrietta Leavitt, and found distances. He did the following. He started looking at further and further galaxies, and looked also at their absorption spectrum. In the column under redshifts here, look at the middle stripe of light, the middle stripe of spectrum. Notice that you can see some absorption lines. Specifically, coming from the left, look for those two lines that are close together. Now look at the second triplet of spectra, in the middle one. The one for Ursa Major, which means that that's a galaxy in the Big Dipper. By the way, it's the same galaxy that in a previous lecture we've seen some variable Cepheid stars in there, so that's guaranteeing that the distance is correct. You can see that those two lines moved a tad to the right. Why? That represents an absorption line that's shifted towards the red. Notice how for Hydra, the one at the bottom, it moved all the way to the right. So the further away the galaxy, the faster it shifts to the red. Now if we remember the idea of the Doppler effect, remember if an ambulance passes you by and with a siren, the siren pitch drops as the waves stretch. If the ambulance moves really fast, the pitch drops further, which means that the redshift, the growing redshift, means that the galaxies are moving further away from us at a faster rate the further away they are. So as usual, I have a couple more questions for you, and I'll give you a few more seconds to try and answer them. Go ahead and read and see if you can get the right answer. Once you're done, check and see if you were right. When Hubble saw the graph that you're seeing in front of you, the further away galaxy, the faster it moves, he found it to be bizarre. Why should galaxies be moving away from us? If you look at particles in a gas, dust in the air, anything, things move away from us, towards us in all directions. Hubble, like Leavitt and Tycho Brahe, was an observer. He wasn't sure why that was. He just kept on measuring very carefully. The further he measured, the more the trend seemed to be correct. The last graph in this picture was done very recently, and it actually extends to 1/10 the distance to the edge of the observable universe. So as usual, I have a couple more questions for you, and I'll give you a few more seconds to try and answer them. Go ahead and read and see if you can get the right answer. Once you're done, check and see if you were right. So why are those galaxies moving away from us faster the further away we are? Most people have an absolutely wrong view of the Big Bang that goes somewhat like the picture right below here. They think that there was a center from which everything exploded. Now, since everything is moving away from us, we have to be in the center of that explosion. Now, for one thing, that's exactly what we moved away from when we did the Copernicus revolution. Earth was in the center before that, then we put the sun in the center. Now, suddenly, we put our galaxy in the center. So that is leaving a bad taste, but there is another problem here. The Hubble law would not be right unless those galaxies that were furthest left first. So the further away galaxies should have different chemical composition of spectra. We don't see that. There are also some physics laws related with explosions that make this very unlikely. So this slide sucks because the Big Bang actually happened everywhere, in every point in the universe at the same time. Now, how can that be? The answer is that we have to use Einstein's general relativity theory. If you remember, that's what we did with explaining black holes. So we explained what happened near black holes, and we saw how the very massive object changes the direction of light. Here is what the universe can do in general, and what the following story does is it's a simplified story that explains this theory. It was developed by Einstein, then by 4 different people: Friedman, Lemaitre, Robertson, and Walker together. But the story is fairly simple. Assume there were 3 galaxies: Adam Galaxy, Eve Galaxy, and a Snake Galaxy. The universe grew to twice its size, but those galaxies remained the same exact size as they were. The distance between them grew from, say, 1 to 2. You can make it 1 megaparsec to 2 megaparsecs. And say that they grew, the universe doubled in 1 unit of time. Let's say 1 billion years. So let's see what Eve's reporting is happening. She says that Adam moved away from her at 1 per 1 billion years. There is 2 minus 1, which is 1 over 1. She looks at the snake and she sees the same thing. From 1 it went to 2, so it grew by 1 in 1. But Adam's telling a different story. He says that Eve is moving at 1 per 1 for him, but the snake is not. The distance to the snake grew from 2 to 4. So it grew in 2 in that one period. So the further away the object is, the snake is further, the faster it moved away from Adam. The universe expanded because energy from the high temperature changed into distances. And that is how Hubble law can work. So as usual, I have a couple more questions for you, and I'll give you a few more seconds to try and answer them. Go ahead and read and see if you can get the right answer. Once you're done, check and see if you were right. So as usual, I have a couple more questions for you, and I'll give you a few more seconds to try and answer them. Go ahead and read and see if you can get the right answer. Once you're done, check and see if you were right. A lot of lecturers use the same exact thing with balloons rather than Adam, even a snake. But you can see that the idea is about the same idea. Distance between two galaxies on a balloon grow from 2 to 4. From 1 to 2 or 2 to 4. Therefore, the further away you are, the faster you move. In 3 dimensions, you can do the same exact thing. That's why we placed those galaxy clusters in this picture in the same exact place, but made the cube in which they are double in size. Same thing. Double in size, the further away the galaxy, the faster it seems to recede from us. And that doesn't matter where we are in a cube, it's still gonna be correct. The 5 pictures in this slide are of the people most important in the development of the expansion of the universe theory. First, of course, on the upper left corner is Albert Einstein, a graduate of Polytechnic in Zurich, no PhD, worked as a patent clerk, got a job as a visiting professor later on, and only after his great discoveries did he get an actual position as a professor of physics. He invented the theory of gravity that includes relativity and E equals mc squared, from which the expansion of the universe came. Second, to his right, is Friedman. He was a young mathematician in Russia just before and after World War I, and he developed the first mathematical expansion of the universe theorem using Einstein's equations. Einstein himself created a model for the universe, but his model was wrong. Next, to the right of Friedman is Lemaitre, who was actually a monk or a clergyman in Belgium. He got his degree in physics, became a clergyman, and then came back to study in Cambridge, and was the one that made the connection that not only is the universe expanding, but it should have been very small, incredibly dense, and hence he called it had the original nucleus. Next after that is Robertson. Robertson was from Washington State, and he came up with the correct mathematics that would combine Einstein's and Friedman's ideas. Later on, after he published his famous papers, he became a worker for the State Department and then the CIA, basically figuring out the effects of weapons systems. It started just before World War I, but he continued all the way until he passed away in the 60s. Last one, Walker, an Englishman, he was the one that put all of the proper math together so that the model works. Yes, it ends up still being Adam, Eve, and a snake. But guess what? If we did the full math here, it would take at least another 4 semesters. Now I take that diagram that I've shown you of the expansion of the universe causing the faraway galaxies to move faster, and go not to 1/10 the size of the universe, but further out still. There is a situation here that we have to take into account. Is the universe expanding at a constant rate exactly? You have to take a couple things into account. First is that the speed of light is finite, so we see the very far away galaxies as they were billions of years ago. And the other thing is that if the universe, for example, is accelerating its expansion or slowing down its expansion, at the very end of the Hubble diagram there'll be very different kinks to the graph. That's what is on the right side. Now, of course, if the universe is going to slow down its expansion, the right hand side diagram is a very intuitive picture of that. The blue circle represents a universe that expands and then collapses on itself. And then the pink one is a universe that would basically remain exactly in the borderline. And the next one over is a universe that is basically never going to collapse back on itself. We are not even in the last one. Ours is not even in there. Our universe is actually speeding up its expansion at the moment. This diagram actually gave Adam Rees and Saul Perlmutter the Nobel Prize in Physics for 2012, I believe. Basically, this is a diagram that's very similar to the Hubble diagram. It's, if you may notice, it's got this insert, and this insert has lines that tell you that the universe is actually accelerating its expansion. Basically, think back to Adam, Eve, and a snake. After one interval, 1 grew to 2 and 2 grew to 4. After 2 intervals, basically what you will have is that the growth will actually become larger. So 2 would not grow after 2 more intervals to 4, but actually 2 would grow to 4 point something, and 4 would grow to 8 point something. So 2 grows to, let's say, 4.2, and 4 grows to 8.4, etc. So the expansion is speeding up. This does not make a lot of sense as far as the physics is concerned, because we expect gravity to always be effective and eventually pull things back. However, that's the way the universe is. The third huge column on which the Big Bang Theory stands is the abundance of elements isotopy. Everywhere you look at those spectra of stars and galaxies, like the Harvard calculators did, but for galaxies. And you see how much helium is in each galaxy on average, not in the evolved stars, but in the youngest stars, in the oldest stars, the stars that never exploded. So that abundance of elements should be the same only if the beginning of the universe was about the same everywhere. What it means is that in the first 3 minutes or so of the universe, as we go backwards, the temperature is just right for making helium from hydrogen, the same way as they're being made in the middle of the sun. So we had a little bit of creation of helium from hydrogen in the beginning of the universe. Now, if that's the case in a galaxy in one direction and in a galaxy in another direction, that's evidence that both of them were the same. Now we're talking, of course, about not very active galaxies, but galaxies where we have mostly stars that have not even burned the original core of hydrogen into helium, so that we can look at their outside and see matter as it was 13.7 billion years ago. And since in that case all of the elements seem to be the same in all directions and actually not that different at very different distances, that's a huge support for the Big Bang theory, the fact that the universe was hot and dense at a certain point. Now here comes a huge fourth column that supports the Big Bang theory and a question that's related. In 1965, the forefathers of satellite phones, Penzias and Wilson, were working to see if they can actually broadcast microwave into space. What they were concerned with is that there may be some stars or active stars, etc., that would make disturbances. So they tried to find out what the frequency was of those stars. To their amazement, they found out that microwave hiss is coming. Okay, it's microwave, it's light, of course. We're not talking about any sound. So it's light with very long waves near the radio, called microwave, and in all directions they're aimed their weird antenna at. It's called the shoehorn antenna at. They found radiation, and that radiation was in the form of a black body with its peak. If you remember, the peak of black body radiation tells us, for example, if it's blue, it's incredibly hot. If it's red, it's less hot. If it's infrared, it's less hot. Well, this was as if there was a black body out there radiating at about 2.7 above absolute zero. Here is the spectrum of a black body from whatever it is that Penzias and Wilson discovered. Now, the wavelength is in centimeters or hundreds of meters. Compare that with wavelengths of hundreds of nanometers for red, orange, yellow, green, blue, indigo, violet. That means it's a way longer wavelength. What it is a wavelength that has been greatly stretched. As you go further and further from Earth, you're going to galaxies that move faster and faster away, until you reach the time when galaxies actually formed, and even beforehand, when the whole universe was brilliant with light, shining at around 4,000 degrees. At that time, what happened was that the radiation was freed to go. So we're seeing the time the radiation is freed to go. There were basically the whole universe was almost as hot as the surface of the sun, and then it started clumping to form galaxies. to first order, to first degree, this is incredibly uniform. In every direction Penzias and Wilson looked, they found the same amount of radiation coming from that echo of the time when the universe was hot and dense. So incredibly uniform and smooth that you can't see variations that are larger than 1 part in about 100,000. Still, if we are to find evidence that from that echo galaxies formed, we want to find those 1 part in 100,000 kind of variations in the microwave. The instruments we are seeing, the instrument in the previous slide was from the COBE satellite, then there came WMAP satellite, then Planck satellite. All of them were done so that you could measure those tiny fluctuations in that echo from the early universe. Precision is so important that 2 of those 3 satellites were not placed in Earth's lower orbit, but at what's called the Lagrangian point, which is basically at the shadow of Earth, far from sunlight, in a way that it's very dark and very cold, and we can see very, very precise variations. In this and the next few pictures, we see this again panorama of the whole universe, the whole night sky and day sky, basically the whole sky, but we're seeing the fluctuations. It's not easy to determine those fluctuations. For one thing, we are moving relative to that background. So that red and blue at the very top is the very first thing that we have to subtract in order to find those variations in the microwave background. Then if you look in the second picture, we have to erase that dominant feature in the middle, which is our own Milky Way galaxy. Then we're left with the variations. This picture is from the first COBE satellite that came up in 1991. This picture that was already doctored for our own motion, and the Milky Way was subtracted. That's the picture that shows those tiny variations, 1 part in 100,000 or less. And it's from WMAP Wilkinson Observatory that was looking at those variations. The first results came in 2003. So we had COBE in 91, WMAP in 2003. Planck results were only up last year. So those tiny variations that you're seeing here in more detail came from the Planck satellite. Why are these so important? Let's put those variations and look at what are the variations like, and that would come in the next slide. When we look at the fluctuations as function of size, which means let's look at large fluctuations, smaller fluctuations, tinier fluctuations, etc. See if they basically are disappearing. What these fluctuations are telling us, and this is kind of like maybe striking a gong for the whole universe, or striking a drum, some sort of a standing wave of the whole universe, that's responsible for those variations which will create on the very small scales galaxies and clusters of galaxies. Here in the results from the Planck Observatory, angular size of 0.07 degrees corresponds to about 10 to 20 million light years, which means that includes us, Andromeda, a few other galaxies, so somewhere in between our local group of galaxies and a slightly larger cluster. So, even at that level we can see that there are fluctuations, therefore they could give rise to galaxies. How exactly they're giving rise to those galaxies can be told from this graph. In a sense, we call it something like the bottom down, meaning huge galaxies form first, then they collide with each other and create most of the galaxies that we see today, the disk and elliptical galaxies. Let's reverse the process then and see how the universe is doing its thing. The universe was incredibly smooth, dense, hot, with tiny variations. Those variations grew into huge superclusters in which lots of stars formed, including such large stars that they ended up as black holes. Those black holes would be in those huge galaxies. Some of those galaxies merged, creating other galaxies. And as the universe was expanding, galaxies interacted less and less. Basically, the uniformity, the smoothness has gone way and way less, and the universe is less and less smooth as time goes by, until at present not only do we have galaxies, stars and planets, but we also have smaller details such as continents, countries and people. In terms of time, basically the distance between two objects has been growing dramatically from the time of the Big Bang, which we basically just reverse the time and go until two atoms were joined at a heap, and until the present day. I kind of like that picture because it gives you sort of a feeling of the fact that the universe not just was hot and dense, but that it grew in size and got reduced in temperature exactly at the same rate. But what is the geometry of the universe? And you're asking yourself, what do you mean by that? Universe is three-dimensional, isn't that right? Well, not exactly. It's not at all clear. You may remember in the beginning that I said that the observable universe could be just part of an infinite universe, but doesn't have to be. It could be that the observable universe is what we call a closed sort of space. Probably the best example is Meissner space. Meissner space is a weird space. Basically, you go straight till you find yourself in the same place, or you look straight and you see the back of your head. Only, of course, you would die because it takes 20 billion years until light would come and see the back of your head. You look up, you see your bottom of your feet. But unlike the case near a black hole, you look to the left, you see the right. So in all three dimensions, you can close a circle in a sense. That is a just possible geometry for space. There's also something called the settled space and flat space. Flat space is just what you're thinking of when you're thinking of three-dimensional space. As I mentioned earlier, the universe is accelerating its expansion. The main culprit that is responsible for accelerating the expansion is now assumed to be something called dark energy. We don't know what it is, and we're very uncomfortable with it, but it constitutes about 70% of everything. Of the rest, more than 20%, more than 29% are what's called dark matter, which means material that doesn't shine and is not protons and neutrons and electrons. And only a fraction is matter like us. We still don't know what dark matter is, we don't know what dark energy is. Therefore, we are in many ways still in the dark on how that universe of ours is functioning. This is not at all close to our understanding of how the solar system works. Late last year I was in a conference that took this picture below and made it even a tad tighter. Basically, we have some independent confirmation about those two weird energies, negative energy and dark energy, that still are making us see a lot of evidence that that's the case. We still don't know what makes it work. This last slide is part of research that I started about 15 years ago, exactly when that evidence for the acceleration of the universe was first presented. If you are interested in it, I would be happy to speak with you about it. For the time being, this is the end of our last lecture. I had a great time talking with you over on the phone. I enjoyed a lot of your comments on the forums, and I had a very interesting time preparing this online course. Interesting in great ways, in not so great ways. But all in all, it was definitely an enriching experience, which I'm going to make a lot of use of. I thank you very much for all of your suggestions, and I wish you great luck in the final. Please take your time on the final. All of the slides will be available. Questions are from both the book and from my own test bank, and I would expect you to work on it on your own, of course. I don't doubt you would do that. Again, I hope you'll have a fantastic time for the rest of the summer, and as I do finish each of my classes at Baker University, I'll do so here. May you live long and prosper.